So welcome everyone for today's session, which is topic number 4-1. Today we will start overview on bridge analysis and also how to do calculation for dead load on bridges. So pretty much we are done with the three first topics, and we concluded the last session with Mike Colmo on topic number 3. We will have topic number 4, which is bridge analysis. It will take us almost 5 sessions. So for bridge analysis, we need to understand that bridge structure analysis is different from building because the structure system is different. So for example, here, we need to know what kind of loading that we are experiencing. As we mentioned before in the bridge loading, we have now trucks and moving loads, which is very much not common in building. But in bridges, you need to, in order to do your bridge structure analysis, you have to assume that the bridge, which is a fair assumption, will behave elastically under gravity load. So no cracking, no sign of yielding, etc. And also, you need to determine for sure the normal forces P or M, shear moment for all components, such as bridge decks, longitudinal girders, bend caps, column, and footing. You also need to have a very realistic and rational mathematical model. To do so, there is some type of loading that, as we described last few lectures, that you have dead load, which is DC, dead load of component, or DW, the dead load of wearing surfaces. And also you have live load plus impact, which come from HL93, or your permanent loading truck per your state. And you also have so many different type of loading, wind load, earthquakes, etc., and also temperature loading. We will focus most of our calculations in this class on the first two, dead load plus live load, and also temperature loading. So for structure analysis, we have a theory that we use we use usually small deflection theory, which is very adequate for analysis of beam type girder. We assume that the loads or the structure system, even with deflection, is straight. There is no deflection, and deflection will not control your structure analysis. We have another method, which is large deflection theory, which has to be counted for nonlinearity during deflection. We also assume that the couple resulted from tension and compression forces. Imagine if you have a beam, steel girder, and you have compression and tension. We assume that the distance between the couple, the forces, compression and tension, are fixed relative to each other for when the bridge actually deflect, for the small deflection theory. In order to do the mathematical models, you have to get the loads, which we describe. We have to get for all the girders and structure system for superstructure, the area, the inertia, and the length. So at the end of the day, your girder has to be modeled with modulus of elasticity based on the material, the area based on the material, the inertia, and for sure the length will control your shear moment. You also need to get, as we discussed modulus of elasticity and what kind of boundary condition that you have, hinge, fix, or ruler. So in general, the two quantities EA and EI is governing your axial deformation and flexural deformation. We have a method to consider when you do bridge analysis. The first one is Griffin method, which basically either grillage or 3D models or finite strip methods or software, right? CSI Bridge, etc. Which basically depend on also 3D modeling, 3D finite element modeling. We also have what's called the stick model or spine model, where you lump sum all the inertia moments or moment of inertia around X, Y, and Z in a stick model. For example, if you have a box girder, you say you have a box girder. So you have to calculate for this box, sorry for the drawing, the area and inertia around X and Y and Z, and you model it as a stick model or what's called spine model with these properties and the length, and you get the boundary condition based on how the superstructure is connected to substructure, which is from the column bases and abutment, and also the connection between them. So we will go through an example here. If you click on this website is very useful in terms of using a spine model for box girder. So what you need to do is you will choose how to get the properties of box girder by defining the depth of the box girder. So your depth is total depth. The width of the box girder, which is the total width of the girder. The number of girders that you have, in this case you have 2 exterior, interior, so 4 girders. Also, the slope of the exterior girders, you can define them here if you have a slope. You also will define the thickness of both exterior and interior girders, which is the thickness of the girders, which is you very much did during your homework too. Top slab, which is a deck thickness, and bottom slab, which is a soffit thickness, which is also you defined during your project, not project, class. You also have the overhang length and the thickness of overhang from the tip and from the exterior girder. The unit that you select here will be feet or inches or millimeter or centimeter or meter. Use feet or inches, and also get the output. So output will be area, solid area, which is the entire area with voids. So solid area is the area plus the void area, which is for some torsional calculation. You also have the moment around X, Y, and the torsional calculation, and this will help you to do the spine model. For the dead load, let's go through an example. This is a call out from previous slides in topic number 3, that the DC and DW are related to dead load of component or dead load of wearing surfaces, future overlay, and this table will show you how to get the unit weights of each material. So you see, in always reinforced concrete, we use 150 pound per cubic feet. Steel is 490 pound per cubic feet. Approximately, your box girder will have linear cube per linear foot around 10 to 15, and the steel girder between 4 to 6. Here, just slide to enlarge this table from section 3 in AASHTO. And for wearing surface, we assume that every 15 to 20 years, we will be replacing the overlay. So we will have asphalt to concrete overlay, which around 3-inch thickness, with bituminous wearing surface unit weight 140 pound per cubic feet and 3 inches of overlay. Your overlay load is 35 pound per square feet area. So every foot of your structure, foot by foot, will weigh 35 pounds. So in this method, we will have to do structure analysis superstructure. You have to get shear and moment for every 10th of a girder length, or 10%, reaction support, and also calculate the deflections. The camber is a measure that we use usually with a dead load DC to counter the effect of deflection. So assuming under DC loading, let's say this is a DC load, you will have a deflection, let's say 2 inches. You will form your superstructure so that it actually create a camber in your structure upward deflection. So when we apply DC, it became flat and it deflects only for additional load like DW and live loads. In order to get this information, you need to do in the spine model, you need to get, for example, if you have a box girder, you need to know information about modulus of elasticity, which is this is the equation. In AASHTO, you use kip and inch, so KSI or kip. So this equation 33,000 gamma to the power 1.5 as square root of prime C. For 4 KSI, you can apply this equation and you end up having 34 KSI modulus of elasticity of concrete. And for steel, you know, it's 2800. Structural steel is 28,000, and for reinforcing steel is 29,000. So concrete creeps over time and under constant load, which is always going to be DC, permanent loading. So you will have what's called modulus of elasticity long term, which is equal to the modulus of elasticity divided by 1 plus eta t, which is function of time. The maximum value of zeta is 2, so you can safely use third of modulus of elasticity to count for creep. Let's go through an example here. Let's say this is your problem. You have 2 interior girders and 2 exterior girders. So stepwise, you need to calculate loads on exterior and interior. What you usually use tripotary area for your loading. So for interior girder, you have to get the factor that has the area of the interior respect to the area of the entire box, similarly to this interior girder and exterior girders. And now after you calculate everything per box, you can multiply this time this factor, and this will convert it to your girder. So let's go through an example. This is the same example that we have showed in the Bridge Automation website a few slides ago. The same cross section for a span is 150 feet. So you got from this program that the area around 74 feet square. You know the unit width of concrete is 0.15 kip per cubic feet, which is now give you 11.1 kip per foot. You multiply unit width of concrete times the cross section of your section, it gets you the load uniform and along the direction of the bridge because you multiply that in the cross section. In DW, the overlay unit weight was 35 pounds per square feet, which is 0.035 kip per cubic square feet. You need only to multiply times one dimension, which is the width of your bridge, which was 45, to get the load in the longitudinal direction. So, and you have also the inertia calculated here as 413, and your f prime feet to the power 4, and f prime 0 for KSI. So now we know from the left side, this is from the previous slide, that your WDC, WDW is 11.1 and 1.58 kip per foot respectively. What you can now calculate for the maximum moment will happen in the for simply supported beam at half the span. You can use WS square over 8 for the moments for both DC and DW. So you multiply the weight or the uniform load from DC 11.1. You multiply times 150 square over 8, you get 31,219. And for DW, you get 4,444. And the shear is WS over 2, is just a simple supported beam. Your moment is WL square over 8. And your shear is equal to almost to the reaction, which is WL square over 2. So WDO for the shear, you got your shear value is 833 due to DC, and DW is 119. Remember, this is per box. Now we need to get it per girder. Let's say we need to calculate for interior girder. Again, we are repeating the information from the previous slide as index for us. So you know that your girder width, which is the spacing from this example, is 12 feet 8 inches. The total depth is 6 feet. You can calculate the area of the deck, area of the soffit, and area of the web. So in this case, you know that your deck or top slab is 12.67, which is the width, times the thickness, 0.75. It gives you 9.5 feet square. The soffit, which is the bottom slab, is 12.67 times 0.54, which is the thickness of this example. It gives you area of 6.84. The area of the web is actually, you get the 6 feet depth, you subtract, so this is your 6 feet, you subtract the depth of the top slab and the bottom slab, which is 0.75 and 0.84. So the depth of your web is now 4.71. You multiply times 1, which is the width of the web, 1 foot. You get the area is 4.71. The total area now is the area of the deck, soffit, and girder is 21.8, and you know the area of the entire box was around 74. You can now divide the two numbers and you get the factor for interior girder and exterior girder. Interior will be the same, 0.285, and exterior 0.215. They all should add to 1. And all you need to know now of those factors and this moment and shear per box, you need to multiply to get the moment DC dW per girder, to multiply the moment per box times the girder factors, and you get your DC and dW. And now you can use your load combination 1.25 the DC and 1.5 dW to get the factor load for the girder, which is in this case for the moment is 13,022 kip per foot per girder. And similarly, you can do it for shear, and it will end up 384 kip per girder. You also need to calculate the camber or deflection, so you can calculate the camber. You usually use it with DC. So your DC load, this is deflection of simply supported beam, which is usually 5WL square, sorry, 5WL to the power 4 divided by 384. Modulus of elasticity times I, and we consider for long term due to creep. So if you use the EC equation from AASHTO, you get around 3834 KSI. If you convert it to KSF, it's around 552,096 divided over 3, give you 184,000 almost KSF. You use the equation, you know 5 is from equation, 11.1 is the DC load, and 150 is the span length L, and 384 is equation factor, and this is the E long term, and the I was 413. You cannot see it here, but it should be 413 feet to the power 4, and your deflection due to dead load will be 11.6 inches, around 1 foot. You have to use it as camber for your box. The other case is the steel girder. In this case, I'm giving you the cross section, and it's made of built up section. You have two overhang of almost 3.5 feet. You have a four girders of 3 spacing of 12 feet, slab thickness of 9.5 inches, total width out to out 43 feet. Roadway width is 40 feet. You have also 1.5 of barrier width. In this case, we don't worry about the weight of the barrier now, but usually the weight of the barrier goes to the first 3 girders. So, but in this case, you don't have more than 6 girders, so you can use the total weight of the barrier and divide over the number of girders to divide between them, the load between them, but we will discuss that later. So basically what you need to do is to get your cross section for your girder. In this case, we have a top flange of a 1-inch plate with 16-inch width. We have web of 48-inch depth and 5/16 thickness, and also bottom flange of 18 inches and thickness of 1 inch and 3/8. We create this table. This table put top flange, width, and bottom flange. The thickness, as you can see here, 1, 5/16, and 1/3/8. The width is the width of your plate, which is 16 in the top flange, 48 for the web, 18 for the bottom flange. You multiply the thickness times the width, give you the area. You sum the area, you got the total area. So you also need to get the depth D, which is the distance from centroid of your plate to the centroid of the web. So in this case, you can have 24.5 for the top flange, because you have 24 to the centroid of the web from the web, and half to the centroid of the top flange. The distance between centroid of the web to centroid of the web is 0. The thickness from the centroid of the bottom flange to the centroid of the web is 24, which is half of 48, plus half the thickness. So you get minus 24.7. We count everything above the centroid of the web as positive. Everything below that is negative. Now you can calculate your AD, multiply area times D. You can sum them up. Now we can calculate AD square, which help you in calculating the inertia, and you also create the inertia around the plate, each plate. So the plate around its centroid would be always pH cube over 12. So for the top flange will be 16, which is the p value. H is 1 to the power 3 over 12, so approximately 1. Similarly, bottom flange, and the web inertia will be high because it's a p is 5 over 16, but h is 48 to power 3 over 12. You add the inertia around the centroid of the plate to the AD square, you get the inertia around the centroid of the web. However, the top plate or top flange and bottom flange are in different size, so the centroid of the section is actually an offset from the web. So that's why you calculate this value, which is summation of A times D over summation of A. That means that you need to lower your neutral axis from the centroid of the web to the center of your neutral axis by negative 3.73 inches. You need to calculate that to offset your inertia too. So now you can calculate y bar times summation AD, and you add them add this two values for the inertia, and you get your final inertia around the centroid of your cross section. Given that you know now all of this good stuff, now we need to calculate the weights, which the weight will be straightforward for easiest interior girder. You have the weight of the plate girder, which is from the area. You multiply the unit weight of the steel. Look through the conversion from 490 per cubic inch feet to inches, because your area is in inches for this plate girder. So it's around 200 pound per linear foot. Area of the deck is 9.5, which is the width of the deck, thickness of the deck, times the width of the deck, which is 12 feet times 150, give you 140 or 1425. The haunch here, you can see 3.5-inch haunch, which is if you have top girder, you have to get a haunch top plate to reach through the thickness of the deck. So in this case, the thickness of the haunch is 3.5 over 12 to convert it from inch to feet, times 16 times 12, which is the width of your top plate, times 150. When you add them all up, you get your WC. Your WC in this case became 2 kips per foot, because you add so many stuff. You add the plate girder weight, which we calculated in the previous slide. We calculate the deck weight, the haunch weight. We also will have cross frames between the girders, which we can assume as 120 pounds per linear foot, and also stay in place form to form the bottom of the slab or the deck, bridge deck, which also make a steel form, which is could be 200 as assumption for now, pound per linear foot. You add them up, you get 2,000 pounds per linear foot, or 2 kips per linear foot. Now you calculate all the DC information. You can now go and calculate your moment and midspan using W squares 2. In this case, we have the span length of 100 feet. So make sure that you use 100 feet for L square over 8 and multiply it times WDC. You get 2,500 kip per foot per girder. And this is for interior girder. And the shear is WL over 2. Your WDC is 2 from this calculation. Your L is 100. Divide by 2, you get your shear as 100 kip per girder. And this is conclude the first presentation with the last slide of calculating the deflection, which is pretty much similar to the box girder. Using to calculate the camber, you need to use the equation 5 for a simply supported girder with uniform load. You have 5 WL to the power 4. Can delete that one. Divide by 384 modulus of elasticity of steel. So this is a mistake. Sorry for that. And times IX. Your W is your WDC, which is 2 kip per foot. Your EC is 29,000 KSI, sometimes 28,000 KSI, converted to KSF. And your inertia, you calculated already as 27,333. You calculated the deflection from this equation. You have the 5, you have the 2, which is the load DC, you have the 100, which is the length, you have 176,000, which is your AS, modulus of elasticity of steel, and you multiply that times the inertia, and you end up having 0.47. Here this is the factor that you convert your inertia from inch to the power 4 to feet to the power 4, which is Kim 1.32. So all the equations here is in kip and foot. So the deflection will be in foot, which is 0.47, which is around 5.67 inches, which is too high, I do believe, in this example. But it has to be cambered up to count for dead load deflections. This concludes today's presentation for topic 4-1, bridge analysis, general and dead load. Next few lecture video will discuss more about influence line for moving loads, and how to calculate a live load per girder using live load distribution factor, and some rules in the AASHTO. And also we can get brief on how the software are used to calculate those deflections and loads. Thank you very much for staying tuned. See you next session.